Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual history of physics contains certain documents that, while brief, function as conceptual fulcrums, pivoting the entire discipline toward new horizons. Max Planck's 19th communication to the German Physical Society, titled Über eine Verbesserung der Wienschen Spectralgleichung, on an improvement of Wien's equation for the spectrum, stands as a paramount example of such a work. Presented in October of that year, this terse, almost provisional, paper is often overshadowed by the monumental theoretical edifice Planck would erect a mere 2 months later. Yet, to appreciate the genesis of the quantum revolution, one must first perform a rigorous internal evaluation of this initial paper on its own terms. This essay will undertake such an evaluation, proceeding section by section through Planck's arguments as he presented them. The focus will remain exclusively on the claims, the methodology, and the physical reasoning contained within this specific text. We will analyze how Planck, working at the zenith of classical physics, constructed a formula of remarkable accuracy, driven by an astute combination of empirical deference, mathematical intuition, and profound thermodynamic insight. The paper reveals a mind grappling with an empirical anomaly not through revolution, but through a conservative, incremental refinement that, with a touch of historical irony, paved the way for the very conceptual overthrow it sought to avoid. It is a masterclass in phenomenological physics, an act of intellectual carpentry that produced a structure so perfect it exposed a fundamental flaw in the bedrock upon which it was. But Section 1, framing the problem as a refinement of existing theory, Planck initiates his argument with a gesture of collegial deference and a precise identification of the problem at hand. He opens by affirming the established success of Wilhelm Wien's spectral distribution law, which had, until that point, represented the most successful theoretical description of blackbody radiation. Planck states that Wien's equation, which describes the energy density of radiation as a function of frequency and temperature, possesses experimental validation in the domain of short wavelengths, or equivalently, high frequencies. This initial claim is foundational to his entire approach. By explicitly circumscribing the region of Wien's law's validity, he frames the subsequent exercise as a modification, an augmentation, an improvement of Verbesserung of an already valuable piece of physics. The intellectual posture is one of conservation and extension. He is building upon the house of Wien, adding a new wing to accommodate fresh data. The fresh data in question came from the recent and famously precise experimental work of Heinrich Rubens and Ferdinand Kerlbaum. Planck alludes to their findings, which demonstrated conclusively that at very long wavelengths and high temperatures, Wien's law failed. In this low-frequency regime, the energy density was found to be directly proportional to the absolute temperature, a relationship which Wien's exponentially decaying function was incapable of producing. Planck's claim, therefore, is that the existing theoretical framework has a well-defined boundary of applicability. His stated objective is to produce a new formula that respects the verified success of Wien's law at one extreme while also accommodating the new empirical reality presented by Rubens and Kerlbaum at the other. The methodology implied by this framing is one of synthesis. He seeks a single, unified expression that can seamlessly bridge two disparate, empirically verified physical behaviors. The paper's opening paragraph thus presents the problem as one of theoretical unification driven by experimental necessity, a classic program within the traditions of 19th century German physics. Section 2. The construction of a limiting case interpolation formula. Having established the problem, Planck proceeds to his central proposal and new equation for the spectral energy density. His presentation of this formula is a moment of profound intellectual dexterity. He introduces what he later famously, and with some modesty, called a happily guessed interpolation formula. The evaluation of this claim requires a close look at the mathematical structure he proposes. Wien's law for the spectral energy density, which we may call U sub nu, took the form U sub nu is equal to a constant, which we can call C1, times the frequency cubed, multiplied by the exponential of the quantity negative C2 times frequency divided by temperature. The critical feature is the exponential term, which ensures the energy density drops off sharply at high frequencies. As observed, the experimental results at low frequencies, however, demanded a linear dependence on temperature. Planck's proposed improvement is mathematically subtle and breathtakingly effective. His new formula, his U sub nu, is equal to the same constant, so 1 times frequency cubed, all divided by the quantity of the exponential of C2 times frequency over temperature, minus 1. The entire innovation resides in the denominator. The genius of this construction lies in its asymptotic behavior. In the high-frequency limit, the argument of the exponential, C2 times frequency over temperature, becomes very large. Consequently, the exponential term itself is a large number, and subtracting 1 from it has a negligible effect. The formula thus gracefully reduces to the form of Wien's original law, preserving its success in the domain where it was known to be correct. In the alternative limit, at low frequencies, the argument of the exponential becomes very small. For a small argument x, the exponential of x can be approximated by the first 2 terms of its Taylor series expansion, namely 1 plus x. Applying this, the denominator becomes approximately 1 plus the quantity C2 times frequency over temperature, minus 1. The ones cancel, leaving a denominator of C2 times frequency over temperature. The full expression then simplifies. The spectral energy density becomes proportional to the constant C1 divided by the constant C2, multiplied by the frequency squared, multiplied by the temperature. This result matches the required linear dependence on temperature and the frequency squared dependence of what would later be known as the Rayleigh-Jeans law. Planck's claim that he has constructed a successful interpolation is therefore entirely valid from a mathematical standpoint. He has engineered a single, continuous function that correctly reproduces 2 different physical laws in their respective regimes of validity. His guess was an act of profound mathematical intuition, guided by the precise requirements of the physical boundary conditions of the problem. Section 3. The crucial turn towards an entropy-based derivation, a mere successful interpolation, however happy, would have remained a piece of empirical curve fitting, a useful but perhaps theoretically shallow exercise. The true depth of Planck's argument, in this October paper, the claim that elevates it far beyond a simple mathematical fix, lies in his immediate effort to ground this new formula in the bedrock of thermodynamics. Planck, a consummate expert in the second law, understood that any legitimate radiation formula must correspond to a consistent thermodynamic description of the radiating system, which he modelled as a collection of electromagnetic oscillators. The connection between the energy of an oscillator and its entropy was the key. Wien's law itself could be derived from a specific assumption about the relationship between the entropy, S, and the energy, U, of a single oscillator. Specifically, it corresponded to the condition that the second derivative of the entropy, with respect to the energy, is proportional to the negative inverse of the energy, that is, d squared s by du squared is equal to a constant divided by u. Planck recognized that to derive his new radiation law, he needed a new, more general expression for this thermodynamic relationship. This is the most abstract and powerful claim within the paper. He proposes a new entropic postulate. He asserts that the second derivative of entropy with respect to energy takes the form d squared s by du squared is equal to a negative constant, alpha, divided by the quantity u multiplied by the sum of a constant beta and u. The seemingly minor modification to the entropy-energy relation is the conceptual core of the work. Integrating this expression twice with respect to energy and applying the fundamental thermodynamic connection between temperature, energy, and entropy, where the inverse of temperature is the first derivative of entropy with respect to energy, one can derive the average energy U of an oscillator. This average energy, when substituted into the relationship between the oscillator energy and the spectral energy density of the radiation field, yields exactly his new radiation formula. The evaluation of this claim is twofold. First, it demonstrates Planck's unwavering commitment to thermodynamic principles as the final arbiter of physical laws. Second, it transforms his interpolation formula from a mathematical convenience into the consequence of a new, posited physical property of radiating matter. He is essentially claiming to have discovered a more fundamental thermodynamic behavior for oscillators. The genius here is the inversion of the problem. Instead of simply presenting a formula that fits the data, he presents a fundamental thermodynamic postulate from which that successful formula can be rigorously derived. This lent his proposal an immense theoretical weight and a sense of physical plausibility that a simple interpolation would lack. Section 4: Empirical corroboration and the emergence of universal constants. The final section of Planck's brief communication deals with the crucial step of connecting his theoretical construction back to the world of experimental measurement. He claims that his formula provides an excellent representation of the observational data. He specifically notes the agreement with the results of Rubens and Kuhlbaum, the very data that had falsified Wien's law and motivated the entire investigation. This claim of empirical adequacy was, of course, immediately verifiable and proved to be astonishingly accurate. The formula fit the measured spectral curves across the entire range of frequencies with a precision that was unprecedented. This perfect correspondence between his thermodynamically derived equation and the exacting measurements from the laboratory provided the strongest possible vindication of his approach. Beyond this immediate empirical success, Planck makes another critical claim regarding the nature of the constants appearing in his formula. The constants C1 and C2 from his radiation law, which are combinations of the more fundamental constants alpha and beta from his entropy expression, are presented as universal constants of nature. This is a point of immense significance. His theory was not just qualitatively correct, it was quantitatively predictive. By fitting his equation to the experimental blackbody data, one could extract precise numerical values for these two new fundamental constants. One of these constants, which would soon be designated as H, became known as Planck's constant. The other would be identified with what we now call the Boltzmann constant, K, providing a new and more accurate method for its determination and, by extension, the calculation of Avogadro's number. The evaluation of this aspect of the paper highlights its function as a powerful new tool for metrology. Planck had not only solved a pressing theoretical puzzle but had also delivered to the experimental community an instrument for probing the fundamental constitution of the universe. The existence and determinability of these universal constants gave his formula a profound sense of reality and importance. It suggested that he had stumbled upon a deep truth about the interaction of energy and matter, even if the full meaning of that truth remained, for a few more weeks, shrouded in the language of classical thermodynamics. The work's claims to be an improvement were fulfilled, as it provided a more accurate, more comprehensive, more fundamentally grounded description of thermal radiation than any that had come. In conclusion, a meticulous evaluation of the internal claims of Planck's October 19th paper, Über eine Verbesserung der Wienschen Spectralgleichung, reveals a work of extraordinary intellectual craftsmanship operating at the apex of classical physics. The paper proceeds with impeccable logic, beginning with a precise definition of an empirical problem, proposing an elegant mathematical solution in the form of an interpolation, and then, most critically, grounding this solution in a new, more general thermodynamic principle concerning the entropy of oscillators. Its final claims of empirical verification and the identification of new universal constants solidified its status as a major scientific achievement. The paper's arguments are entirely self-contained within the framework of thermodynamics and electromagnetism, as understood at the time. It is a testament to the power of that classical framework, demonstrating its ability to accommodate new phenomena through sophisticated modification. The work's profound significance lies in its very success. By producing the exact mathematical form of the black-body radiation law through thermodynamic reasoning, Planck inadvertently created an undeniable explain duma thing to be explained. The perfect formula was now on the table, but its thermodynamic derivation, while brilliant, felt like a redescription rather than a fundamental explanation. The entropy expression he postulated was itself an axiom awaiting a deeper justification. It was the self-imposed intellectual pressure, the need to provide a statistical mechanical basis for his successful entropy formula, that would compel him, in the subsequent weeks, to take the final, revolutionary step. This initial paper, in its conservative brilliance and its complete fulfillment of its own stated goals, thus created the intellectual conditions necessary for the more radical work that would follow, serving as the perfectly constructed classical archway through which the new physics was destined to pass.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.